For as long as human beings have existed, the night sky has never been empty. It has always been crowded with light and with meaning. Before there were telescopes and before there were written words, there were stars scattered across the darkness like distant fires. They did not move like animals, and they did not grow like plants. They remained fixed and silent. That stillness made them feel eternal. To the first humans who ever looked upward, that eternity felt sacred. The sky became a place where gods lived and where the souls of the dead were believed to travel. Across nearly every culture, the stars were turned into stories. A band of light across the sky became a river of spirits. A pattern of bright points became a hunter. A single bright wandering light became a goddess. Even when science began to replace myth, the fascination never disappeared. The tools changed, but the longing stayed. When Galileo first pointed a telescope at the sky, he did not destroy the dream of the heavens. He made it deeper. He revealed that the bright dots were not tiny holes in a crystal dome, but distant suns surrounded by their own worlds. The universe suddenly became far larger and far more mysterious. Every star could be another place. Every faint glow could be another home. As astronomy advanced, this idea only grew stronger. By the time modern physics was born, the cosmos had transformed into an endless ocean of galaxies. Each one held billions of stars. Each star could hold planets. The numbers were so large they almost stopped meaning anything at all. 10 to the power of 11 stars in a galaxy. 10 to the power of 11 galaxies in the visible universe. When people heard those figures, it was easy to believe that life must be everywhere and that reaching it was only a matter of time. This belief became woven into modern culture. Science fiction turned the stars into highways. Rockets crossed between solar systems as easily as ships cross oceans. Humans settled new worlds. Empires rose across the galaxy. It felt natural because the human mind evolved to understand travel across land and sea. When people crossed continents and then crossed oceans, the sky seemed like the next step. If Earth was a shore, then space was simply the next frontier. The 20th century appeared to confirm that dream. In less than one human lifetime, we went from flying in fragile machines made of wood and cloth to placing a human being on the surface of another world. When the first astronauts left Earth orbit and traveled to the moon, the distance felt enormous, but it was conquered. In 1969, humans walked on lunar soil and returned home alive. The images of those missions burned into global memory. A person standing on another world looking back at Earth. A blue sphere hanging in the darkness. It felt like the opening chapter of something vast. If we could reach the moon, then Mars would be next. After Mars would come the outer planets. After that, the stars themselves. But there was something hidden beneath that triumph that almost no one noticed. The moon is far away by everyday standards, but in cosmic terms it is still part of Earth. The average distance between Earth and the moon is about 384,000 kilometers. Light takes just over 1 second to cross that gap. A radio message from mission control to an astronaut on the moon is almost instant. The moon is not another place in the universe. It is a nearby outcropping of Earth. Every Apollo mission was still wrapped inside Earth's invisible protective bubble. Our planet is surrounded by a magnetic field and a thick atmosphere that deflects deadly radiation from the sun and from deep space. The astronauts never left that shield for more than a few days. Even when they were walking on lunar soil, Earth's magnetic influence still reached them. Their spacecraft could talk to Earth in real time. Rescue was at least theoretically possible. If something went wrong, the journey home was measured in days. This is why the moon was the easy part. It felt far, but it was still close. It was not separated from us by the true vacuum of interplanetary and interstellar space. It was still tethered to our world by gravity, by communication, and by protection. We did not step into the ocean of the cosmos. We stepped into a shallow tide pool. The triumph of Apollo created a powerful illusion. It suggested that space was something we were beginning to conquer. In reality, we had only brushed against the edge of our own planet domain. Everything beyond the Moon is separated from Earth by distances that are not merely large, but fundamentally different in nature. They are so vast that the human brain cannot feel them the way it feels a mountain or a sea. They exist on scales that break intuition. Mars at its closest approach is tens of millions of kilometers away. When it is on the far side of the Sun, it is hundreds of millions of kilometers away. A radio signal can take more than 20 minutes to cross that gap. If an astronaut on Mars asks a question, they must wait 40 minutes to hear a reply. That delay alone changes everything. Emergency response becomes impossible. Real-time control vanishes. You are no longer connected to Earth. You are isolated in a way that no explorer in history ever was. And Mars is still our neighbor. The nearest star system beyond our own is Alpha Centauri. It is about 4 light years away. That means light itself takes 4 years to travel that distance. A spacecraft traveling faster than any machine humans have ever built would take tens of thousands of years to arrive. That is not exploration. That is a message sent to a future that will not remember who sent it. The dream of reaching the stars rests on a quiet assumption that distance is just an engineering problem. Build a faster rocket, carry more fuel, use better materials. But space does not obey the rules of human travel. It obeys the laws of physics. Those laws do not care about ambition or imagination. They define what is possible and what is forbidden. The Moon was reachable because it was inside our gravitational neighborhood. Everything beyond that neighborhood is separated from us by an energy wall that rises faster than any technology can climb. Even before we confront radiation and biology and communication, we run into the most unforgiving barrier of all: the sheer cost of moving mass through space. This is where the real story of human limits begins. For every rocket that has ever left Earth, there is a simple and brutal truth hidden inside its engines. To move forward in space, you must throw mass backward. There is no other way. Every kilogram of fuel you carry must also be accelerated along with the spacecraft. That means the heavier your ship becomes, the more fuel it needs. The more fuel it carries, the heavier it becomes. This is not a problem of design. It is a consequence of physics. This relationship is described by the rocket equation. It states that the final speed a rocket can reach depends on how fast it can throw its exhaust backward and how much of its total mass is fuel. What makes this equation cruel is that it grows exponentially. If you want to double your speed, you need far more than double the fuel. You need an amount that rises so fast, it quickly becomes absurd. To reach even a small fraction of the speed of light, you would need a ship that is almost entirely fuel with a tiny payload buried inside. This is why rockets that reach Earth orbit are mostly propellant. The metal and electronics and human crew make up only a small fraction of the total mass. Nearly everything else is burned and thrown away just to reach low Earth orbit. That is the cost of escaping Earth gravity well. And Earth gravity well is gentle compared to the gravity wells of the Sun and the galaxy. When a spacecraft leaves Earth, it does not stop falling. It is always falling around the Sun. To escape the solar system entirely, it must reach a speed that lets it break free from the Sun gravity. That speed is called the escape velocity from the solar system. Near Earth, it is more than 42 km per second. That is more than 150,000 km per hour. Even the fastest probes humans have ever built only barely reach that speed. The Parker Solar Probe is currently the fastest human-made object. It uses repeated gravity assists from Venus and dives close to the Sun to steal orbital energy. At its peak, it will reach around 195 km per second. That is astonishing by human standards. It is also only about 0.065% of the speed of light. At that speed, it would take more than 6,000 years to reach Alpha Centauri. And that probe carries no people. It carries no life support. It carries no shielding. It is a fragile machine built to survive only a few years in extreme heat and radiation. Scaling that to a human mission would require orders of magnitude more mass. Every kilogram of water, air, food, and shielding would multiply the fuel required. Very quickly, the ship becomes so heavy that no conceivable rocket could launch it. Some propose nuclear propulsion as a solution. Nuclear rockets can eject exhaust faster than chemical rockets. That helps. But it does not change the exponential nature of the rocket equation. Even with optimistic designs, a nuclear thermal rocket might reach a few tens of kilometers per second of exhaust speed. That is still nowhere near enough to make interstellar travel practical. To reach even 10% of the speed of light would require a mass of fuel greater than many mountains. Others imagine antimatter drives or fusion engines. These sound powerful, but they face the same wall. Even if you could convert mass to energy with near-perfect efficiency, you still must carry that mass with you. Every gram of fuel must be accelerated along with the ship. The faster you want to go, the more energy you need. The more energy you need, the more mass you must carry. The cycle never ends. This is the energy wall. It is not a technological hurdle. It is a mathematical one. It arises from the way momentum and energy behave in our universe. No clever engineering can make it go away. You cannot cheat the rocket equation. You can only obey it. This is why even reaching the outer planets of our own solar system takes years. Voyager 1 took more than 12 years to reach Neptune orbit distance. And Voyager 1 was launched in 1977. It is still traveling. After more than 4 decades, it has only just left the heliosphere, which is the bubble of charged particles blown out by the sun. It has not reached interstellar space in any meaningful sense. It has simply crossed an invisible boundary. At its current speed, Voyager 1 will take about 70,000 years to reach the distance of Alpha Centauri. That is longer than all of recorded human history. When it arrives, Earth will be unrecognizable or possibly gone. This is what it means to say that speed is the real enemy. Distance in space is not measured in kilometers. It is measured in time. And time is set by how fast you can go. No human technology has ever come close to a speed that makes the stars reachable within a lifetime. The fantasy of interstellar travel ignores this reality. It imagines engines that somehow bypass the need for reaction mass. It imagines ships that glide through space without paying the energy cost. But in the real universe, there is no such thing as free motion. Every change in velocity must be bought with momentum. Every momentum change must be paid for with fuel. The deeper you look, the more unforgiving the numbers become. Even if you could build a ship the size of a city and fill it with nuclear fuel, it would still only crawl across the interstellar gulf. And that is before we even consider what happens to the people inside. Because even if you could find a way to push a human ship to high speed, there is another wall waiting. One written into the fabric of space and time itself. As speed increases, something strange begins to happen. It is not just that fuel becomes harder to carry. Space and time themselves begin to change. This is not science fiction. It is one of the most tested and verified parts of modern physics. According to Einstein's theory of relativity, the faster you move, the slower time passes for you compared to someone who is not moving. At everyday speeds, this effect is too small to notice. At cosmic speeds, it becomes overwhelming. If a spacecraft could travel at 10% of the speed of light, time on board would pass a little more slowly than on Earth. At 50%, the effect would be dramatic. At 90%, it would be extreme. Astronauts might experience only a few years while decades passed on Earth. At first, this sounds like a solution. Perhaps a crew could travel to the stars within their own lifetimes, even if thousands of years passed back home. But this is an illusion. Time dilation does not reduce the energy required to move. In fact, it makes it worse. As you approach the speed of light, your effective mass increases. That means it takes more and more energy to accelerate you further. To reach the speed of light would require infinite energy. This is not a limitation of engineering. It is a law of the universe. Nothing with mass can ever reach or exceed the speed of light. So every interstellar journey is trapped between two impossibilities. If you go slowly, it takes tens of thousands of years. If you try to go fast, the energy required becomes infinite. There is no middle ground where a human ship can cross the stars in a reasonable time. Even reaching 1% of the speed of light would be revolutionary. At that speed, a ship could reach Alpha Centauri in about 400 years. That is still many generations. And 1% of the speed of light is more than 3,000 kilometers per second. No propulsion system ever conceived could push a large crewed spacecraft to that speed. The dream of faster-than-light travel often appears as a way out. Warp drives and wormholes promise to bypass the distance. But every serious examination of these ideas runs into the same problem. They require forms of matter and energy that do not exist or violate known physical laws. They are mathematical curiosities, not engineering blueprints. The universe has placed a speed limit on information and matter. Light travels at that limit. Gravity travels at that limit. Causality itself depends on that limit. To exceed it would break the logical structure of reality. This is why physicists treat faster than light travel as fantasy. When you combine the rocket equation with relativity, the result is devastating. Not only is it incredibly hard to reach high speed, but the closer you get, the harder it becomes. The stars are not just far, they are protected by the geometry of space-time. And even if you could somehow send a ship that far, another problem would emerge. Human bodies are not built for journeys that last centuries. Bones weaken in low gravity, muscles waste away, radiation damages DNA, the immune system collapses. A voyage that takes generations would not deliver living explorers. It would deliver their distant descendants, if anything survived at all. This is the hidden truth behind the dream of the stars. The barrier is not just engineering. It is biology and physics woven together. The universe allows us to look out. It allows us to understand, but it does not allow us to cross its vastness as travelers. The moon was reachable because it was part of Earth domain. Mars may one day be visited because it is still nearby in cosmic terms. But the stars are not neighbors. They are other universes separated from us by oceans of time and energy that no ship can cross. The dream that launched 1,000 rockets was built on a misunderstanding. We thought the sky was an open road. In reality, it is a wall. Everything that has ever moved through space has done so by paying a price. That price is energy. On Earth, we hardly notice it because the air and the ground help us. A bird pushes against the air. A car pushes against the road. In space, there is nothing to push against. To change your speed, you must throw something away from you. That thrown mass becomes your exhaust. It carries momentum in the opposite direction. You move forward. This is not a limitation of rockets. It is how motion works in a universe that obeys conservation of momentum. Every spaceship is a machine that trades mass for motion. That trade is governed by the rocket equation. It does not care if your fuel is chemical, nuclear, or antimatter. It only cares about how fast your exhaust leaves the ship and how much of your total mass is fuel. The equation is merciless. If you want a little more speed, you need a lot more fuel. If you want a lot more speed, you need an absurd amount of fuel. The growth is exponential. That means it quickly outruns anything you can build. Consider a simple example. Imagine a spacecraft where half of its mass is fuel. When that fuel is burned, the ship might reach some speed. If you want to double that speed, you cannot just double the fuel. You must increase the fuel so much that the ship becomes mostly propellant with a tiny payload. If you want to reach 10 times that speed, the fuel mass becomes so large that it exceeds the mass of entire mountains. This is why real rockets are almost all fuel. A launch vehicle lifting a small capsule into orbit is mostly tanks. The engines and structure and crew are a thin shell around a towering column of propellant. Nearly everything is burned away in the first few minutes. That sacrifice is what allows a tiny fraction of the mass to reach space. And this is only for low Earth orbit. To go beyond Earth gravity well, you need more speed. To go beyond the Sun gravity well, you need even more. To go to the stars, you need speeds that are so high the rocket equation becomes a brick wall. Nuclear propulsion is often proposed as the answer. Nuclear reactions release far more energy per unit mass than chemical reactions. That means the exhaust can be thrown out faster. Faster exhaust means you get more speed for the same amount of fuel. This helps, but it does not change the exponential nature of the problem. A nuclear thermal rocket might throw exhaust at about 8 to 9 kilometers per second. That is roughly twice as good as the best chemical rockets. It is impressive. It is also still tiny compared to the thousands of kilometers per second needed for interstellar travel. Even advanced fusion concepts might reach exhaust speeds of a few hundred kilometers per second. That sounds enormous. It is still only a fraction of 1% of the speed of light. To reach even 1% of the speed of light with a realistic payload, the mass of fuel required would be so large it would exceed the mass of large asteroids. There is no launch system in the universe that could lift such a structure. Some designs try to avoid carrying all the fuel by using external energy. Light sails, for example, could be pushed by powerful lasers from Earth. This avoids carrying propellant, but it introduces a new limit. The sail must remain in the beam. As the ship moves away, the beam spreads out. Its intensity drops. The push becomes weaker and weaker. To keep accelerating, you would need a laser array larger than continents producing power greater than all of human civilization. Even then, the sail would only reach a few % of the speed of light. It could not slow down at the destination. It would fly past the target star and vanish into the darkness. The energy wall is not something we will one day engineer around. It is built into the structure of reality. Every kilogram you want to move must be given kinetic energy. That energy grows with the square of speed. To go twice as fast requires 4 times the energy. To go 10 times as fast requires 100 times the energy. When you approach the speed of light, the required energy rises without bound. This is why the universe feels so large. It is not just that the stars are far apart. It is that moving between them is energetically prohibitive. The cosmos is designed in a way that makes isolation the default. We can send small machines outward. Probes like Voyager can drift for eons. But they are not travelers. They are messages in a bottle thrown into a cosmic sea. They cannot carry people. They cannot carry civilizations. The dream of starships fails, not because humans lack imagination, but because the universe charges too high a price for motion. And that price rises faster than any technology can pay. Speed is the true enemy, and it leads us to an even deeper barrier. Everything about interstellar travel becomes more unforgiving as speed rises. The faster you move, the more energy you must pour into your ship. The more energy you pour into it, the more dangerous it becomes to control. At low speeds, space feels calm. At high speeds, it turns violent. Even a grain of dust becomes a bullet. In interstellar space, there are tiny particles drifting between the stars. They are rare, but they are not absent. At speeds of thousands of kilometers per second, a speck of dust has the energy of an explosive. A collision would release more power than a battlefield weapon. No material we know of could survive repeated impacts at those velocities. Radiation also becomes more severe. As a ship moves faster, it plows through a sea of high-energy particles. These include cosmic rays, which are atomic nuclei moving near the speed of light. When they strike matter, they shatter atoms and damage molecules. At high speed, the flux of these particles increases. The ship becomes bathed in a storm of invisible bullets that can penetrate deep into metal and flesh. To shield against this, you would need walls of material many meters thick. That adds mass. More mass requires more fuel. More fuel increases the energy needed. The cycle feeds on itself. Then there is heat. At high speeds, even the thin gas between stars becomes a source of friction. It deposits energy into the ship's surface. Over years of travel, this heating could degrade materials and electronics. Cooling systems would be required. Those systems would need power and mass. All of this makes high-speed flight not just expensive, but fragile. The faster you go, the more violently the universe pushes back. This is why even unmanned probes are designed to travel slowly. Voyager 1 is moving at about 17 km per second relative to the Sun. That is a crawl by cosmic standards. It avoids collisions and reduces wear. At that speed, it will survive for decades. At higher speeds, it would be destroyed long before reaching another star. When people imagine starships, they picture sleek vessels gliding through empty space. But interstellar space is not empty. It is a thin but deadly medium. At low speed, it is harmless. At high speed, it becomes a weapon. This brings us back to relativity. As speed increases, time dilation begins to stretch the journey in strange ways. The crew might age slowly compared to Earth, but the ship still experiences the full violence of the trip. Every collision and every radiation hit happens in its own frame. Time dilation does not protect you from damage. So the idea of racing across the stars by going faster only trades one impossibility for another. You either go slow and take tens of thousands of years, or you go fast and face energies that no structure can survive. This is the second face of the energy wall. It is not just about fuel. It is about survival in a universe that punishes speed. The deeper physicists look into this problem, the more it seems that the cosmos is designed to keep its distant regions apart. It allows light and gravity to cross the void. It allows information to flow, but it does not allow matter to move freely. The stars can see each other, they cannot touch. And if even machines struggle to cross that gulf, humans have no chance. The next barrier is not mechanical, it is biological. Even if a miracle of engineering allowed a ship to reach interstellar speeds, the living beings inside would face a reality far harsher than anything on Earth. Human biology evolved under one constant: gravity. We are built to live on a spinning planet with a thick atmosphere and a magnetic field. Remove those, and the body begins to fall apart. In orbit, astronauts lose bone density at a rate of about 1% per month. Their muscles weaken, their hearts shrink. Their vision changes as fluids shift inside the skull. These effects appear after only a few weeks. After months, they become severe. After years, they could become fatal. Artificial gravity might help, but building a rotating habitat large enough to avoid motion sickness adds even more mass and complexity. Then there is radiation. Outside Earth, magnetic shield. The body is exposed to cosmic rays and solar storms. These particles punch through tissue and damage DNA. They increase the risk of cancer and cause long-term neurological harm. No known material can block them completely without being extremely thick and heavy. Water and lead can help, but you would need walls meters deep. That is not practical for a spacecraft. On a journey that lasts decades or centuries, the accumulated radiation dose would be lethal. Even if the crew did not die quickly, their cells would mutate. Birth defects would rise. The genetic integrity of the population would erode. This is why some propose A-generation ships. The idea is that a large population could live and die aboard a vessel while their descendants eventually reach another star. But this faces its own problems. A closed ecosystem must recycle every molecule of air and water. It must produce food forever. Even small imbalances can cause collapse. On Earth, such systems are stabilized by vast oceans and forests. A ship has none of that. Genetic diversity would also decline. In a small, isolated population, random changes can quickly dominate. Harmful mutations can spread. Over hundreds of generations, this can lead to severe health problems or extinction. The ship itself would have to function for thousands of years without outside repair. No machine in human history has ever done that. Even the most reliable technologies fail eventually. Metals corrode, electronics degrade, software breaks. In the deep vacuum of space, repairs would become harder with time, not easier. So even if you could overcome the energy wall and the speed limit, you would still be left with a vessel that must be a perfect world. It must be a self-contained Earth. It must never fail. There is no evidence that such a thing is possible. This is why the stars are not waiting for us. They are separated from us by more than distance. They are separated by the requirements of life itself. Earth is not just a place. It is a system, a delicate balance of gravity, atmosphere, magnetism, and biology that has no easy replacement. We can leave it for a while, we can orbit, we can visit nearby worlds, but to abandon it and cross the interstellar void is to step into a realm where every law of nature turns against us. The energy wall was only the beginning. The biological wall is just as final. Space does not behave the way human intuition expects. On Earth, distance is something you can always overcome with enough time and enough effort. Walk long enough and you cross a continent. Sail long enough and you cross an ocean. But space is not built on that kind of geometry. It is built on space-time, and space-time has limits. The most important of those limits is the speed of light. Light in a vacuum moves at about 300,000 kilometers per second. Nothing that has mass can move that fast. This is not because of engineering. It is because of how energy and momentum are woven into the structure of reality. As an object approaches the speed of light, its energy requirement rises without bound. To reach the speed of light would require infinite energy. Infinite energy does not exist. This means every star is separated from every other star by a minimum amount of time. Alpha Centauri is 4 light years away. That means light itself takes 4 years to travel from there to here. No signal can be faster. No ship can be faster. 4 years is the absolute best case. In practice, any real spacecraft would take far longer. Even at 10% of the speed of light, which is wildly beyond any known propulsion system, the trip would take about 40 years. At 1%, it would take 400 years. At the speeds of our fastest probes, it would take tens of thousands of years. Time dilation changes how that journey is experienced by travelers, but it does not change what happens to the ship. At high speed, the crew might age slowly, but the hull still collides with dust and is bombarded by radiation for the full duration of the trip. The universe does not care how old you feel. It cares how long you are exposed. This creates a cruel paradox. To make the trip short for the crew, you must go faster. But going faster makes the environment more deadly. To survive, you must go slower. But going slower makes the trip impossibly long. Relativity turns the stars into islands separated by oceans of time. Even if you could cross those oceans, you would never truly arrive in the same era you left. You would step into a future that has forgotten you. This is why interstellar travel is not like exploration on Earth. It is not about distance, it is about time. The universe is not just big, it is old, and it makes you pay that age in full. The deeper you look into relativity, the more it becomes clear that the universe is designed to keep distant places apart. Space and time are not separate. They are part of a single structure. When you try to move through space faster, you also move differently through time. That trade cannot be escaped. At everyday speeds, this effect is tiny. But at the speeds required for interstellar travel, it becomes dominant. Suppose a spacecraft could somehow reach 90% of the speed of light. From the point of view of the crew, time would slow dramatically. A journey that takes many years on Earth might feel like only a few months on board. This sounds like a gift, but it is also a trap. The ship would still need the same enormous amount of energy to reach that speed. It would still need to survive the full length of the journey measured in Earth time, and it would still emerge into a future where everyone it ever knew is gone. There is also the problem of turning around. To slow down at the destination, you must shed the same amount of energy you use to speed up. That means you need just as much fuel to stop as you did to go. If you do not have it, you will simply fly past the target star and never return. This doubles the already impossible fuel requirement. You must carry enough energy not only to accelerate to high speed, but also to decelerate. Otherwise, your ship is not a vehicle. It is a bullet. Some imagine using the destination star gravity or magnetic field to brake the ship. But at relativistic speeds, these effects are tiny. The ship would pass through the system too fast to be captured. You would need a massive artificial braking system waiting at the other end. That defeats the point of exploration. This is why realistic interstellar mission designs all collapse under their own mass. When you add up the fuel for acceleration, the fuel for deceleration, the shielding, the life support, and the structural reinforcement, the ship becomes so heavy that no propulsion system can move it. Relativity is not just a speed limit. It is a mass multiplier. As you go faster, your inertia increases. That means it takes more force to change your speed. The universe resists your motion more strongly the harder you push. This is why the stars appear so close, yet remain so far. You can see Alpha Centauri in the sky. You can measure its light. You can know its planets. But you cannot go there in any meaningful sense. It is locked behind a wall of space-time. When people talk about colonizing the galaxy, they are imagining a universe that does not exist. They are imagining a place where distance is just a number. In reality, distance is a physical barrier enforced by the deepest laws we know. The cosmos is not a stage built for travelers. It is a tapestry woven for light. And even if you could somehow cross that tapestry, there is still the question of whether anything alive could make the journey. The final cruelty of relativity is that it makes the idea of return almost meaningless. Suppose a crew leaves Earth at near light speed. They travel for what feels like 5 years on board and reach another star. On Earth, centuries have passed. Every person they knew is gone. Every nation has changed. Their language may no longer even be spoken. Even if they could send a message back, it would take years to arrive. They would be ghosts from a forgotten age. This breaks the concept of exploration. Exploration implies a connection between the explorer and the society that sent them. Interstellar travel severs that link. It creates a permanent divide in time. For machines, this might not matter. For humans, it matters deeply. We are social creatures. Our identities are built from relationships. A journey that disconnects you from your entire species is not a voyage. It is an exile. This is why the universe feels empty, even though it is full of stars. The distances do not just separate locations. They separate histories. The dream of leaving Earth has always been tied to the idea of expansion. But relativity turns expansion into fragmentation. Each star system becomes its own isolated timeline. Communication becomes delayed by years. Coordination becomes impossible. A civilization spread across the stars would not be a civilization at all. It would be a scattering of disconnected worlds drifting through time. And this is only the physics of motion. We have not yet touched the deeper problem of survival. Even if a ship could move, and even if time dilation could make the journey feel short, the environment between the stars is hostile beyond imagination. The next barrier is not speed, it is the human body. The human body is a machine built for one very specific environment. It evolved under the pull of Earth gravity beneath a thick blanket of air and within the protective field of a magnetic shield. Every cell, every bone, and every organ assumes those conditions. When you remove them, the system begins to break. In orbit, astronauts experience this almost immediately. Their muscles weaken because they no longer have to support their own weight. Their bones lose minerals and become fragile. Blood and other fluids shift toward the head, causing swelling and changes in vision. Even the heart begins to shrink because it no longer has to pump against gravity. These effects do not stop. They continue as long as the body remains in low gravity. After months, the damage becomes serious. After years, it may be irreversible. There is no evidence that a human can live a normal lifespan in weightlessness. Artificial gravity could help. A rotating spacecraft could create a force that mimics gravity. But to avoid dizziness and nausea, the rotation must be slow and the radius must be large. That means the ship must be enormous. The larger it is, the more mass it has. The more mass it has, the harder it is to move. The energy wall returns. Radiation is an even greater threat. Outside Earth's magnetic field, the body is exposed to high-energy particles from the sun and from deep space. These particles can pass through metal and flesh. They damage DNA and increase the risk of cancer. They also damage the brain and nervous system. There is evidence that long-term exposure can cause cognitive decline. On a trip to Mars, astronauts would already receive a radiation dose near the safe lifetime limit. An interstellar journey would deliver many times that amount. There is no known way to block this radiation without surrounding the crew in thick layers of material. Water and certain metals can absorb some of it, but not all. To reduce the dose to safe levels, you would need walls several meters thick. That adds enormous mass. The immune system also weakens in space. Microgravity changes how cells function. Astronauts become more susceptible to infections. On a long mission, a simple illness could become fatal. Then there is reproduction. No human has ever conceived or given birth in space. We do not know how embryos develop in low gravity or under constant radiation. Animal experiments suggest serious abnormalities. A generation ship would need to rely on healthy reproduction. There is no evidence that this is possible beyond Earth. The idea of a closed population surviving for centuries inside a spacecraft is not just an engineering problem. It is a biological gamble with no proven solution. Earth is not just a place we live. It is a system that supports life in ways we barely understand. The atmosphere protects us. The magnetic field shields us. The gravity shapes our bodies. The biosphere recycles our waste and produces our food. A ship must replace all of that perfectly forever. No experiment has ever demonstrated a closed ecosystem that can do this. Even small test habitats on Earth have struggled. Tiny imbalances grow, species die, systems collapse. In deep space, there would be no rescue, no resupply, no escape. This is why the human body becomes a prison in the void. We are adapted to one world. Everywhere else is hostile. And even if you could somehow keep people alive, the machines that support them face their own battle. Machines in space live in an environment that slowly destroys them. On Earth, equipment is surrounded by air and kept within a narrow temperature range. In space, there is vacuum, extreme cold, intense heat and radiation. Every component is under constant stress. Electronics are especially vulnerable. High-energy particles can flip bits in memory and damage circuits. Over time, this causes errors and failures. Spacecraft use hardened electronics to reduce this, but nothing is immune. The longer a mission lasts, the more likely something critical will break. Lubricants evaporate in vacuum. Materials become brittle. Metals fatigue. Plastics crack. Solar panels degrade as radiation damages their structure. Batteries lose capacity. No system stays perfect forever. On Earth, when something fails, we repair it. In deep space, there is no warehouse of spare parts. There is no team of engineers. Everything must be carried from the start. But carrying spares adds mass. Mass adds energy cost. Again, the cycle returns. For a mission lasting decades, this is already a problem. For one lasting centuries, it becomes fatal. A single failure in a critical system could end the entire ship. This is why even our best probes are designed for limited lifetimes. Voyager 1 has survived for decades, but its instruments are slowly failing. Its power source is weakening. Within a few more years, it will go silent. An interstellar ship would have to remain functional for far longer than any human-built system ever has. It would need to survive a constant bombardment of radiation and micrometeoroids. It would need to maintain life support perfectly for generations. There is no evidence that such reliability is achievable. So, the biological prison is reinforced by a technological one. Humans and machines are both fragile. The universe between the stars is relentless. This is why interstellar travel is not just difficult. It is likely impossible in any practical sense. We can imagine it. We can write stories about it. But the physical reality does not bend to imagination. The next barrier is even more subtle. Even if you could send a ship, it would be alone. Completely alone. Isolation is not just psychological. In space, it is physical. Communication depends on signals that move at the speed of light. As distance increases, so does delay. At Mars, the delay can reach more than 20 minutes. At the outer planets, it can be hours. Between stars, it becomes years. This means an interstellar crew could never speak to Earth in real time. They could not ask for help. They could not receive instructions. Every message would be a time capsule from the past. If something went wrong, the reply would arrive long after the crisis was over. In effect, the crew would be completely on their own. They would not be part of human civilization. They would be cut off from it by time. This has profound consequences. Exploration relies on feedback. Data is sent home. New plans are made. Corrections are applied. None of that is possible when the delay is measured in years. An interstellar mission would be blind. It would launch with a plan and then follow it for decades without knowing if Earth even still exists. This is another way the universe enforces isolation. It does not allow distant parts to coordinate. It forces every region to become its own island. When people imagine humanity spreading across the stars, they imagine a connected empire. In reality, it would be a collection of disconnected worlds drifting through time. Each one would diverge culturally and biologically. They would become alien to each other. The idea of a unified interstellar civilization is incompatible with relativity. The speed of light makes sure of that. So when we say the universe resists exploration, we mean something deeper than distance. It resists connection. It allows us to observe, but not to interact. This is the final aspect of the biological prison. Humans are not just bodies. We are social minds. We depend on communication. In deep space, that lifeline is severed. The stars may be beautiful, but they are silent. Between the stars, there is no shelter. There is no atmosphere to slow particles. There is no magnetic field to deflect them. There is only a thin but relentless storm of radiation and debris moving at extraordinary speed. To human senses, interstellar space feels empty. To a machine traveling through it for years, it is a grinding storm. Micrometeoroids are fragments of rock and metal no larger than grains of sand. They drift through space at high speed. A spacecraft moving through this environment encounters them head-on. At interstellar velocities, even a tiny particle carries enormous energy. A collision can punch through metal like a bullet. On Earth, we protect vehicles with thick armor and active defenses. In space, every kilogram of shielding adds to the mass that must be accelerated. There is no free protection. A ship designed to survive for decades would need to be wrapped in layers of material. That makes it heavier. That makes it slower. That increases its exposure time. Again, the cycle closes. Radiation is an even greater enemy. Galactic cosmic rays are atomic nuclei accelerated by supernova explosions. They travel near the speed of light. When they strike electronics, they can knock atoms out of place. This creates defects in semiconductors. Over time, this degrades performance and causes failures. Even the most hardened electronics accumulate damage. Errors increase, circuits fail, memory becomes corrupted. A mission lasting centuries would face an overwhelming accumulation of faults. Temperature swings are another problem. In deep space, a surface exposed to the sun can become extremely hot. A surface in shadow can become extremely cold. These rapid changes cause materials to expand and contract. Over time, this leads to cracks and structural weakness. Vacuum itself is destructive. Certain materials outgas. Lubricants evaporate. Seals fail. Without atmosphere, some chemical bonds become unstable. Everything ages faster. This is why spacecraft are designed for limited lifetimes. Even the most robust probes are not expected to function forever. They are built to gather data for years and then die. An interstellar ship would need to be immortal. It would need to resist every one of these processes for longer than any machine has ever existed. There is no evidence that such durability is possible. Technology does not like the void. It decays in it. As machines degrade, their complexity becomes a liability. A simple object like a rock can survive in space for millions of years. A spacecraft cannot. It relies on thousands of interconnected systems. Each one is a point of failure. Over time, the probability that something breaks approaches certainty. Consider power. Most deep space probes use radioisotope generators that convert heat from decaying elements into electricity. These slowly lose power as the radioactive material decays. Solar panels lose efficiency as radiation damages them and dust accumulates. There is no infinite power source. An interstellar ship would need energy for lighting, heating air circulation, water recycling, computing, and propulsion. Every one of those systems depends on a continuous supply of power. Even if you started with a vast nuclear reactor, it would not last forever. Fuel rods degrade, structural materials weaken, control systems drift. In a closed system, there is no replacement. Software is another silent threat. Programs contain errors. Over time, memory corruption and bit flips accumulate. Without constant updates and maintenance, the software that controls life support, navigation, and communication would slowly diverge from its intended behavior. Eventually, it would fail in unpredictable ways. Human operators could attempt to fix these problems, but they too would be limited by fatigue, illness, and death. On a mission lasting generations, knowledge would be lost, manuals would decay, skills would erode. The ship would become a technological ruin still moving through space. This is not speculation. It is what happens to every complex system given enough time. Entropy always wins. The interstellar void is not just hostile, it is patient. It does not need to destroy a ship quickly. It only needs to wait. This is why sending machines to the stars is already barely feasible. Sending people with them multiplies the difficulty beyond reason. The dream of a starship that travels forever is a story. The reality is a machine slowly falling apart in the dark. And as it falls apart, it becomes harder and harder to communicate with anyone else. Would you like me to continue to part 3 of this chapter? When communication begins to fail, isolation becomes complete. Antennas degrade, power drops, signal strength weakens. Over interstellar distances, even a perfectly functioning transmitter would struggle. Signals spread out as they travel. Their intensity falls with the square of distance. By the time a radio wave reaches another star, it is buried in cosmic noise. This means an interstellar ship would gradually disappear from the universe of information. Even if it survived physically, its voice would fade. It would become a silent, drifting relic. This is the final way space destroys technology, not with a single blow, but with slow erasure. The farther you go, the harder it becomes to be heard. Eventually, you are alone. This is why the stars are not just distant. They are disconnected. Even if every technological and biological problem could somehow be solved, there would still be one barrier that no invention can overcome: distance itself. In space, distance is not just how far something is, it is how long information takes to travel. And information can never move faster than light. On Earth, distance feels flexible. A message can cross the planet in less than a second through fiber optic cables and satellites. The world feels small, but this illusion is created by technology working inside a tiny cosmic bubble. Outside that bubble, the universe enforces its own scale. When a spacecraft travels to Mars, radio signals take anywhere from 4 minutes to more than 20 minutes to arrive. This means real-time conversation is impossible. Every exchange is slow and awkward. Emergency instructions arrive too late. Human intuition breaks because humans are wired for immediate feedback. Now imagine a ship traveling to another star. At a distance of 4 light-years, a message takes 4 years to reach Earth. The reply takes another 4 years to come back. A single question and answer cycle takes 8 years. If something goes wrong, the crew cannot ask for help in any meaningful way. They must solve every problem alone. This changes the nature of exploration. Every mission in human history has relied on support from home. Even the most remote polar expeditions could eventually receive supplies or rescue. In interstellar space, There is no such possibility. A ship is cut off not just by distance but by time. This also means that control from Earth is impossible. You cannot pilot a ship across the stars by remote command. You cannot guide a landing. You cannot adjust course based on new data. By the time information arrives, the situation has changed. An interstellar mission becomes a pre-programmed fate. Whatever decisions were made at launch will echo forward for decades or centuries. Any mistake becomes permanent. This makes the problem of navigation terrifying. Space between stars is not empty. It contains gas dust and gravitational fields that slowly deflect a ship. Over long times, small errors grow large. A slight misalignment at launch could mean missing the target star by millions of kilometers or more. Without real-time correction, the ship could drift into nothing. Then there is the question of arrival. Suppose by some miracle, a ship reaches another star system. It must identify planets. It must choose a target. It must slow down and enter orbit. All of this must be done autonomously. Any failure means the ship either crashes or flies past forever. Human crews could try to manage this, but they would be doing so with instruments that may have degraded over decades. They would be navigating a system no human has ever seen, and they would be doing it without any guidance from Earth. Distance does not just separate places, it separates responsibility. Once a ship leaves the solar system, it becomes its own isolated civilization. It must carry not only people and machines, but all the knowledge and culture needed to survive. Over generations, that culture will change. It will diverge. The crew descendants will no longer think like the people who launched the mission. Their priorities will shift. Their loyalty to Earth will fade. This means that even if a generation ship arrived, it would not be an extension of humanity as we know it. It would be something new, something shaped by isolation and survival. Earth would be a legend, not a home. Distance also affects science. Data sent back from an interstellar probe would take years to arrive. By the time scientists analyze it, the probe could already be dead. There would be no way to ask follow-up questions. Exploration becomes a one-way broadcast, not a dialogue. This is why even robotic interstellar missions are limited in what they can achieve. They can take pictures, they can send measurements, but they cannot adapt to surprises. They cannot explore in the human sense of the word. The universe enforces this silence through the finite speed of light. It makes sure that no two distant places can ever truly be connected. And this leads to a deeper truth. Colonization is often imagined as a solution to these problems. Spread out, build new worlds. But distance makes that idea collapse. Colonization sounds like an answer to fragility. If one world fails, another survives. But this logic only works when the colonies remain connected. On Earth, every colony in history was supported by ships and communication. They could trade, they could share technology, they could help each other recover from disaster. Interstellar colonies would not have that luxury. Once a colony is separated by light years, it is effectively alone. If a disease appears, it cannot receive medicine from Earth. If a famine strikes, it cannot import food. If a technological system fails, it cannot request replacement parts. It must survive entirely on what it can produce itself. This requires a level of self-sufficiency that no human society has ever achieved. Modern civilization depends on vast global supply chains. Even small communities rely on trade. A star colony would have to mine, refine, manufacture, grow, and repair everything it needs from scratch. That includes computers, medicines, metals, plastics, and complex machinery. The knowledge required to maintain all of this would have to be preserved perfectly across generations. Any loss could be fatal. A broken piece of technology that no one knows how to fix could end the colony. Genetic isolation adds another layer of risk. A small founding population would have limited genetic diversity. Over time, inbreeding and random mutations could lead to health problems. Without new people arriving, the population could decline or collapse. There is also the problem of planetary environments. Most planets are hostile. They have toxic atmospheres, extreme temperatures, or crushing gravity. Even if a habitable-looking world is found, it may have microbes that are deadly to humans, or a climate that is unstable. Terraforming is often proposed as a solution, but terraforming a planet means changing its entire atmosphere and climate. That requires energy and resources on a scale far beyond anything humanity has ever managed. It would take thousands of years, even under ideal conditions. During that time, the colony would have to survive in sealed habitats vulnerable to failure. A single breach could kill everyone. All of this makes interstellar colonization not a backup for Earth, but a gamble with extremely low odds. You are trading one fragile world for another that is even more fragile. Earth is not just habitable. It is unusually stable. It has a magnetic field. It has a large moon that stabilizes its tilt. It has plate tectonics that recycle carbon. It has oceans that regulate temperature. These features work together to keep the climate within a narrow range suitable for life. No other known planet has this combination. So the idea that humanity can simply move elsewhere if Earth fails is not supported by physics or biology. The universe does not provide ready-made replacements. Distance ensures that any colony would be isolated. Physics ensures that building and maintaining one would be extraordinarily difficult. Biology ensures that survival would be uncertain. This is why the stars are not an escape. They are a mirror that shows us how rare and precious our world is. There is one final aspect of distance that is often overlooked. It changes the meaning of existence itself. When a group of humans leaves Earth and cannot return, they are no longer part of a shared story. They become a branch that grows away from the tree of humanity. Over time, their language will change, their beliefs will change, their bodies may change as they adapt to a new world. Eventually, they will no longer be us. They will be something else, born from us, but not connected to us. This is not a moral problem. It is a physical one. When information takes years to travel, cultures diverge. When people cannot interact, societies separate. This has happened many times on Earth across oceans and continents. In space, it would be far more extreme. So even if interstellar colonization were possible, it would not preserve humanity. It would fracture it. The dream of spreading through the galaxy assumes a unity that physics does not allow. The speed of light enforces isolation. It turns every star system into its own island. The more we understand this, the clearer it becomes that space is not a frontier in the historical sense. It is not a place where explorers can go and return. It is a one-way boundary. And beyond that boundary lies a universe that is indifferent to our survival. This brings us to the next, and perhaps most invisible danger of all: the radiation that fills the cosmos. A colony in space is not simply a group of humans living somewhere new. It is a closed world that must replace an entire planet. Every breath of air, every sip of water, and every bite of food must come from inside the system. Nothing can be taken for granted. On Earth, we forget how much work the planet itself is doing for us. The oceans absorb heat and carbon dioxide. Forests release oxygen and lock away carbon. Microbes recycle waste into nutrients. The climate distributes energy from the equator to the poles. Gravity holds the atmosphere in place. The magnetic field shields life from radiation. All of these systems work together without pause. A space colony has none of that. It must create artificial versions of every planetary function using machines and a few fragile biological species. This is not an engineering challenge in the ordinary sense. It is a challenge of recreating the entire biosphere inside a metal shell. Closed-loop life support systems have been studied for decades. On paper, they appear simple. Plants take in carbon dioxide and release oxygen. Humans do the opposite. Waste can be broken down by bacteria and turned back into nutrients for plants. Water can be filtered and reused. But in practice, these systems are unstable. Tiny imbalances grow over time. A small excess of carbon dioxide can slowly poison the air. A slight drop in oxygen can impair thinking and eventually kill. A buildup of trace chemicals can damage organs. Even on Earth, with unlimited sunlight and access to the outside environment, such systems struggle. Experiments designed to seal humans inside artificial ecosystems for long periods have shown how unpredictable they are. Crop failures occur, oxygen levels drift, unexpected chemical reactions change the air. People become sick. The system requires constant adjustment by experts who have access to outside resources. In deep space, there would be no outside. Food production is one of the most difficult pieces. Growing plants requires light, nutrients, and carefully controlled temperatures. Artificial light consumes enormous amounts of energy. Plants also need soil or hydroponic solutions that must be chemically balanced. A small shift in nutrient ratios can stunt growth or kill crops. On Earth, farmers can recover from failure by importing food or changing crops. In a star colony, a single agricultural collapse could lead to starvation. There is also the issue of pests and disease. In a closed environment, a fungus or insect that attacks crops could spread rapidly. There would be no natural predators to control it. Chemical pesticides could damage human health or disrupt the ecosystem further. The colony would have to fight its own biology just to survive. Water recycling is another point of failure. Every person uses water for drinking, washing, and sanitation. That water becomes contaminated with chemicals and microbes. It must be purified perfectly. Filters clog, membranes degrade, bacteria evolve. A failure in the water system could poison everyone. Then there is waste. Human waste contains pathogens and chemicals that must be broken down. This is done on Earth by enormous natural systems. In a colony, it must be done by tanks of bacteria and chemical reactors. If those fail, waste builds up and becomes toxic. All of these systems are interconnected. A failure in one affects the others. This creates feedback loops that can spiral out of control. A slight drop in plant growth reduces oxygen. Lower oxygen stresses people and machines. Stressed machines fail more often. That leads to less maintenance. That further degrades the system. This is what makes self-sustaining colonies so difficult. They must be stable not just for a year or a decade, but for centuries. Even a tiny long-term drift can accumulate into disaster. On Earth, we are protected by scale. The planet is large. If one forest dies, others survive. If one river is polluted, others remain clean. A colony has no such buffer. It is all or nothing. This is the first reason why colonization is not a real solution. A space colony is not a new Earth. It is a fragile experiment that must never fail. A second barrier to self-sustaining colonies is genetic. Life on Earth is stable because it is vast and interconnected. Billions of humans mix their genes across continents. Countless species interbreed across enormous populations. This genetic diversity protects against disease and harmful mutations. In a closed colony, that diversity disappears. A star colony would begin with a small group of founders. Even if that group numbered in the thousands, it would still represent only a tiny slice of human genetic variation. Over generations, random genetic changes would accumulate. Some of these changes would be harmful. In a small population, they can spread quickly simply by chance. This process is called genetic drift. It can lead to increased rates of inherited disease, infertility, and developmental problems. On Earth, such effects are diluted by migration and large populations. In a sealed colony, there is no new blood. The population becomes its own closed genetic experiment. Over hundreds of years, this can lead to serious health problems that cannot be fixed. There is also the problem of evolution under strange conditions. Low gravity radiation and artificial environments would place new stresses on the human body. Traits that are neutral or even harmful on Earth might become more common. The population would slowly diverge from baseline humanity. This might allow survival, but it would also create beings that are biologically adapted to artificial worlds, not to Earth. Psychological strain compounds this. Humans evolved in open landscapes under natural skies. In a sealed habitat, every horizon is a wall. Every breath depends on machinery. People know that one failure could kill everyone. Over generations, this creates a constant background of stress. Conflicts become more intense. Small disagreements become existential. Social stability becomes as important as engineering. A colony must avoid violent sabotage and breakdown. It must maintain education governance and cooperation forever. History shows how difficult this is even on a planet with abundant resources. In space, the margin for error is zero. Children born in a colony would not choose that life. They would inherit it. They would never see a real sky or feel natural gravity. Their entire world would be artificial. Some might rebel. Some might damage critical systems. A single act of sabotage could doom everyone. Then, there is the loss of knowledge. Over centuries, languages change. Records degrade. Skills are forgotten. A complex technological society must constantly educate new generations to maintain its infrastructure. In a small, isolated population, this becomes harder. A lost manual or a misunderstood procedure could lead to irreversible failure. All of this means a self-sustaining colony must not only be biologically stable, but culturally perfect. It must avoid war inequality and collapse for longer than any human society has ever managed. Earth civilizations rise and fall. Empires collapse. Technologies are lost and rediscovered. But Earth itself continues. A colony has no such safety net. If its civilization collapses, everyone dies. This is why, even if humans could reach other stars, they could not build enduring societies there. The conditions required are far stricter than anything we have ever achieved. The universe does not make room for fragile worlds. There is one final weakness in the idea of self-sustaining colonies that overshadows all the others. It is the problem of resources. A colony must not only recycle what it has, it must also replace what wears out. Metals corrode, plastics become brittle, electronics fail, filters clog, seals leak. Every machine eventually breaks. On Earth, when something breaks, we mine new materials. We manufacture new parts. We replace old systems. A colony on another world or in deep space would have to do the same. That means it must have access to a complete industrial supply chain. It must be able to mine or refine metals, produce plastics, fabricate microchips, and build precision machinery. That requires an entire industrial civilization inside a tiny closed world. The energy needed for this would be enormous. Smelting metal requires high temperatures. Manufacturing electronics requires clean rooms and complex chemicals. Producing plastics requires hydrocarbons. A colony would need a source of all of these. If it lacks even one critical material, it could not maintain its technology. Most planets are not rich in accessible resources. Many have surfaces covered in ice or toxic compounds. Mining in low gravity is difficult. Dust and debris float and contaminate machinery. Even if resources exist, extracting them safely and efficiently would be a constant struggle. This means a colony must be placed on a world with not just tolerable conditions, but abundant, easily accessible resources. Such worlds appear to be extremely rare, and even if one were found, the colony would still be vulnerable to disaster. A meteor impact, a volcanic eruption, or a climate shift could wipe out its infrastructure. On Earth, such events are absorbed by a global civilization. In a single colony, they could be fatal. So the idea that humanity can spread out and become safe by moving to the stars is backwards. The more isolated a population is, the more vulnerable it becomes. Earth is resilient because it is large and diverse. A space colony would be small and fragile. This is the deep reason why the universe does not offer easy second chances. The laws of physics and biology conspire to make isolated worlds unstable. We are not meant to be scattered across the cosmos. We are meant to be held together by one planet. The universe is not empty. It only looks empty because human senses are blind to most of what fills it. Between the stars, there is a vast ocean of invisible energy. This energy is not heat or light in the ordinary sense. It is radiation, a constant rain of particles moving at extraordinary speed. On Earth, we are protected from it by a remarkable coincidence of nature. Our planet has a thick atmosphere and a powerful magnetic field. Together, they form a shield that bends and absorbs most of this incoming storm. Without that shield, the surface of Earth would be lethal to complex life. Cosmic radiation comes from every direction. Some of it is born in the sun, thrown outward by solar winds and violent eruptions. Some of it comes from distant supernova explosions that happened millions of years ago. Some of it is produced near black holes and neutron stars where matter is accelerated to nearly the speed of light. These particles do not fade away as they travel. They cross the galaxy for millions of years, striking anything in their path. When one of these particles hits matter, it does not gently bounce off. It slams into atoms with enough energy to tear them apart. In human tissue, that means broken DNA strands, damaged cells, and altered chemistry. Most of the time, the body can repair this damage, but in deep space, the damage happens faster than it can be fixed. Errors accumulate, cells begin to malfunction. Cancer becomes almost inevitable. On Earth, this danger is largely hidden. The magnetic field guides charged particles around the planet, sending them harmlessly toward the poles where they create auroras instead of killing cells. The atmosphere absorbs most of what remains. By the time radiation reaches the ground, it is weak enough that life can survive. This is why life could emerge here at all. In space, that protection is gone. The moment a spacecraft leaves Earth's magnetic shield, it enters a different universe. Every square centimeter of its hull is struck by high-energy particles every second. Over time, those particles damage the structure at the atomic level. Metals become brittle, plastics weaken, electronics suffer microscopic defects that grow into failures. For humans, the effect is far worse. Each cosmic ray that passes through the body leaves a trail of destruction. It punches through cells, breaks DNA, and creates secondary particles that cause even more damage. A single particle can damage dozens of cells along its path. In low Earth orbit, astronauts already receive far more radiation than people on the ground. On a trip to Mars, the exposure would be close to the maximum safe lifetime dose. In interstellar space, it would be many times greater. This radiation does not come in neat bursts. It is constant. Day and night, there is no difference. There is no shelter. Even thick metal walls provide only partial protection. Some particles are so energetic that they pass through meters of solid material as if it were air. This means a starship is never truly safe. It is always being slowly irradiated from every direction. Over months, the crew cells accumulate damage. Over years, the risk of cancer rises. Over decades, the probability of survival falls towards zero. The cruel irony is that radiation becomes worse the faster you go. At high speeds, the ship plows into the radiation field more violently. Particles strike with even greater energy. The universe does not merely sit there. It resists motion. This is why the radiation storm is not just a side effect of space. It is a fundamental barrier to leaving Earth. It punishes distance. It punishes time. It punishes speed. And it never stops. Radiation in deep space is not uniform. It is chaotic. Some regions are relatively calm. Others are saturated with particles that were hurled outward by ancient cosmic catastrophes. A spacecraft moving between the stars would pass through these invisible clouds without any way to see them coming. There are no warning signs. The particles arrive at the same moment the information about them does. You cannot dodge what moves at the speed of light. One of the most dangerous sources of radiation is the sun itself. Although it seems gentle from Earth, the sun is a violent star. It constantly releases charged particles into space in what is called the solar wind. At times, it unleashes enormous eruptions known as solar flares and coronal mass ejections. These events can release more energy in a few minutes than all of human civilization produces in years. When that energy reaches space, it becomes a torrent of high-energy protons and electrons. On Earth, these storms create beautiful auroras. In space, they create deadly radiation floods. Astronauts outside Earth's magnetic field during a strong solar event could receive a lethal dose in hours. There would be nowhere to hide. Even thick spacecraft walls provide only limited protection. Interstellar space adds another layer of danger. There are cosmic rays from outside the solar system that are far more energetic than anything produced by the sun. These particles were accelerated by exploding stars and by matter falling into black holes. Some carry so much energy that a single one can do significant damage to tissue and electronics. Unlike solar radiation, which comes from one direction, cosmic rays come from all directions. A spacecraft cannot turn away from them. It cannot shield one side and leave another exposed. It is immersed in a three-dimensional storm. The biological consequences are severe. Studies of astronauts show that high-energy particles can penetrate the brain and disrupt neural pathways. This leads to changes in memory, attention, and mood. Over long periods, this could impair judgment and personality. A crew exposed for decades could slowly lose the cognitive ability needed to maintain their ship. Cancer risk is even more dramatic. On Earth, background radiation causes a small percentage of cancers. In deep space, the dose would be so high that nearly everyone would develop cancer if they lived long enough. Even if treatments existed, they would be difficult to administer in a closed environment with limited medical resources. Reproduction becomes even more uncertain. Radiation damages sperm and eggs. It increases the risk of miscarriage and birth defects. A generation ship bathed in cosmic radiation would be a genetic experiment with unknown and likely disastrous results. This is not speculation. We already know that radiation damages DNA. We already know that space increases mutation rates. We already know that shielding cannot eliminate the most energetic particles. So when people imagine living among the stars, they imagine a vacuum. In reality, they would be living inside a storm that never ends. There is a deeper problem hidden inside radiation exposure that goes beyond individual health. It affects the stability of any living system over time. Life depends on the reliable copying of genetic information. DNA must be duplicated with extraordinary precision. Even small error rates can accumulate into serious problems over generations. Radiation increases those error rates. In a normal environment, cells have repair mechanisms that correct most mistakes. But high-energy particles cause complex damage that is difficult to fix. They break DNA in multiple places at once. When this happens, the repair systems can make mistakes. Mutations slip through. In a large population on Earth, these mutations are diluted. Harmful ones are often lost. In a small closed population, like a star colony, they can spread. Over generations, this leads to a genetic load that weakens the entire group. Fertility drops, disease increases. Eventually, the population may not be able to sustain itself. Radiation also changes the microbes that would be essential to a closed ecosystem. Bacteria and fungi recycle waste and support plant growth. Expose them to high radiation, and they mutate rapidly. Some may die, others may become aggressive or toxic. The carefully balanced microbial communities inside a habitat could collapse. Plants too are affected. Radiation damages their DNA and their ability to photosynthesize. Growth slows. Crops become less productive. In a system that depends on every plant for food and oxygen, this is catastrophic. The result is that radiation slowly destabilizes the entire biosphere of a space colony. Even if everything is carefully designed at the start, it will drift as radiation alters the biology inside. There is no stable endpoint. This makes the idea of a long-lived space habitat even more unrealistic. It would not just have to maintain machines. It would have to constantly fight the genetic decay of every organism inside. Machines also suffer from radiation in similar ways. High-energy particles knock atoms out of place in semiconductors. This creates defects that change how circuits behave. Over time, memory becomes unreliable, sensors drift, computers crash. Without constant replacement and repair, these systems will fail. Radiation is therefore not just a threat, it is a universal agent of decay. It works on all matter, biological and technological alike. In deep space, there is no refuge from it. One of the most unsettling aspects of cosmic radiation is how little control there is over it. On Earth, we build shelters against storms because storms can be seen coming. We have weather satellites and warning systems. In space, radiation storms arrive at the speed of light. There is no advance notice. When a distant star erupts or when the sun releases a massive flare, the radiation reaches a spacecraft at the same time the information about it does. There is no time to react. This means any deep space crew lives under constant existential risk. A single extreme solar event could deliver a fatal dose. Even if it does not kill outright, it could damage the nervous system or reproductive cells in ways that doom future generations. Some have proposed building shelters inside spacecraft where crew could hide during radiation storms. But these shelters would need to be surrounded by meters of dense material. That adds enormous mass, and even then, the most energetic particles would still get through. The unpredictability of radiation also makes mission planning impossible. You cannot schedule extravehicular activities. You cannot rely on quiet periods. You are always gambling with your health. For machines, the problem is similar. A burst of radiation can flip thousands of bits in memory at once. It can corrupt data and crash control systems. A single event could cripple navigation or life support. This is why radiation-hardened electronics are used in space. But even these have limits. Over long missions, the cumulative damage builds up. The cosmic radiation storm is therefore not just a background hazard. It is an active threat that can strike at any time without warning. Earth is protected from this chaos. Space is not. When all of these effects are considered together, the conclusion becomes stark. The universe is not a gentle place where life can simply spread if given enough technology. It is a high-energy environment that constantly works to erase complexity. Earth is an extraordinary exception. It is wrapped in layers of protection that make long-term stability possible. Remove those layers and life begins to unravel. The cosmic radiation storm is one of the most important of those protective differences. It means that even if a ship could reach another star, and even if a colony could be built there, it would exist in an environment that is far more hostile than anything on Earth. Its people would be aging faster at the cellular level. Their DNA would be under constant assault. Their machines would be slowly failing. Their ecosystems would be drifting out of balance. This is why Earth is not just a starting point. It is a sanctuary. It is one of the few places in the galaxy where the radiation background is low enough and stable enough for complex life to persist over billions of years. The farther we go from it, the more the universe reminds us that it was never designed for us. When humans imagine the universe, they tend to picture a grand ocean filled with countless islands, each one a potential home. There are hundreds of billions of stars in our galaxy alone. There are trillions of galaxies in the observable universe. With numbers that large, it feels natural to assume that life must be common. But numbers alone do not determine habitability. Conditions do. Life is not simply a matter of having a planet. It is the result of a long chain of unlikely circumstances, lining up just right and remaining stable for billions of years. Break any link in that chain, and the world becomes sterile. Most of the universe is immediately lethal to complex chemistry. The space between galaxies is close to absolute zero and filled with energetic radiation. There is no shelter. Molecules cannot easily form. Any complex structure is slowly shredded by high-energy particles. Inside galaxies, conditions are not much kinder. Stars are born in violent clouds of gas and dust. Many of them are massive blue giants that burn furiously and die young. These stars pour out intense ultraviolet radiation that strips atmospheres from nearby planets. When they explode as supernovae, they flood surrounding space with lethal radiation and heavy elements traveling at enormous speed. A planet within a few light years would have its surface sterilized. Smaller stars live longer, but bring their own dangers. Red dwarf stars are the most common type in the galaxy. They are cool and dim, but highly unstable. They produce frequent flares that can be thousands of times more powerful than anything our Sun produces. A planet in the habitable zone of a red dwarf must orbit very close to the star. That makes it vulnerable to these flares. Over time, the atmosphere can be stripped away, leaving the surface exposed to space. Even if a planet survives its star, it must also survive itself. Many worlds are geologically violent. They have runaway greenhouse effects or frozen surfaces. Some are covered in lava oceans. Others are crushed under atmospheres hundreds of times thicker than Earth. Some have no magnetic field, and so their atmospheres are slowly blown away by stellar winds. Earth avoided these fates through a rare combination of circumstances. It formed with just the right amount of water. It developed a molten core that created a magnetic field. It acquired a large moon that stabilized its tilt and moderated its climate. It has plate tectonics that recycle carbon and regulate temperature. Its sun is stable and long-lived. These factors are not guaranteed. They are accidents of formation. When scientists search for exoplanets, they often focus on the habitable zone. This is the region around a star where liquid water could exist on the surface. But this is only the first filter. A planet can be in this zone and still be completely hostile to life. It might lack an atmosphere. It might be tidally locked with one side always frozen and the other always scorched. It might be bombarded by radiation. It might have poisonous chemistry. The universe does not favor life. It tolerates it in rare pockets. Earth is one of those pockets. It is not a typical planet. It is an exception. When astronomers catalogue the planets they find around other stars, the pattern is unmistakable. Most worlds fall into categories that are fundamentally hostile to life as we know it. Many are super-Earths with gravity so strong that any atmosphere becomes crushing. Any organism would be flattened. Others are mini-Neptunes with thick envelopes of hydrogen and helium that create pressures and temperatures far beyond biological limits. Some are ocean worlds where water covers the surface to depths of hundreds of kilometers, leaving no land and no stable cycling of nutrients. Then, there are the hot worlds that orbit close to their stars. These planets are baked by intense radiation. Their surfaces can be molten. Their atmospheres are often stripped away or turned into toxic clouds of sulfur and carbon dioxide. Life as we understand it cannot function there. Cold worlds are no better. Far from their stars, planets become frozen. Water becomes ice. Chemical reactions slow to a crawl. Even if liquid water exists beneath an icy crust, it is isolated from the energy needed to sustain complex ecosystems. Earth sits in a narrow window, not just of temperature, but of chemistry. Its atmosphere is rich in nitrogen and oxygen. Its oceans are not too acidic. Its surface pressure allows liquid water. Its gravity holds onto gases without crushing everything. Each of these conditions must be met simultaneously. The odds of all of this happening together are extremely small. The more we learn about planetary formation, the clearer this becomes. Planets form from chaotic disks of dust and gas. Their final properties depend on countless random events, collisions, migrations, gravitational interactions. Most outcomes are hostile. Even when a planet starts out promising, it must remain stable for billions of years. Life takes time. It took Earth nearly 4 billion years to produce complex organisms. During that time, the planet could not be sterilized by massive impacts or catastrophic climate shifts. It could not lose its atmosphere. It could not be bathed in intense radiation. It had to remain within a narrow range of conditions for eons. That level of stability is rare in a universe full of violence. This is why, even though there may be many planets, there are very few that are truly habitable. The universe is not a garden. It is a desert with a few scattered oases. Even when all of the physical conditions appear to be right, there is still no guarantee that life will emerge. Chemistry does not automatically turn into biology. The transition from simple molecules to self-replicating systems is one of the great mysteries of science. We do not know how it happened on Earth. We only know that it did. The early Earth had liquid water energy sources and a rich mix of chemicals. Yet for hundreds of millions of years, there was no life. Then at some point, a chain of reactions crossed a threshold. Molecules began to copy themselves. Natural selection began. From that moment on, the planet was changed forever. But this may not be easy to repeat. It may require extremely specific conditions. It may require rare catalysts or environments that only exist on certain worlds. It may require long periods of stability without interruption. Many planets may have water and energy and still never develop life. They may remain sterile for billions of years. Even if simple life emerges, the leap to complex life is another barrier. For most of Earth history, life was single-celled. Multicellular organisms appeared only after oxygen built up in the atmosphere. That required photosynthetic organisms to evolve and then survive for hundreds of millions of years. Without that oxygen-complex, animals would never have existed. So a planet must not only develop life, it must also develop the right kind of life. It must have organisms that transform the atmosphere. It must avoid catastrophic extinction events. It must maintain stability long enough for complexity to grow. The chain of requirements becomes longer and more fragile with every step. This is why when scientists talk about the rarity of life, they do not mean that life is impossible. They mean that it is improbable. It requires many things to go right for a very long time. The universe is old and large, which means some worlds will beat the odds, but most will not. Earth did. That makes it extraordinary. Even after complex life appears, it remains vulnerable. Planets are not static. Their climates shift. Their stars change. Their orbits evolve. A world that is friendly today can become hostile tomorrow in cosmic terms. On Earth, mass extinctions have wiped out most species multiple times. These were caused by asteroid impacts, volcanic eruptions, and climate shifts. Yet Earth recovered because it is large and diverse. Life found new niches. Evolution continued. On a smaller or less stable world, such events could end life permanently. A single asteroid impact could sterilize the surface. A runaway greenhouse effect could boil away the oceans. A collapse of the magnetic field could allow radiation to strip the atmosphere. Stars also change over time. As they age, they become brighter. This can push planets out of the habitable zone. A world that once had oceans may become a desert. A world that was once frozen may briefly thaw and then overheat. Red dwarf stars in particular are dangerous. They flare violently for billions of years. A planet close enough to be warm is also close enough to be blasted by radiation. Even if life somehow survives, it would be under constant stress. All of this means that even planets that start out promising may not stay that way long enough for complex life to emerge. The universe does not provide stable platforms. It provides temporary windows. Earth happens to be in one of those windows. It is not guaranteed to last forever, but it has lasted long enough for intelligence to arise. That is rare. When all of these layers are put together, the picture becomes clear. The universe is not structured in a way that favors life. It is structured in a way that produces vast amounts of energy and chaos. Stars explode. Galaxies collide. Radiation floods the void. Planets are thrown into extreme orbits. Stability is the exception, not the rule. Earth is not a typical outcome. It is a lucky one. It exists in a calm region of a quiet galaxy orbiting a stable star with just the right mass and chemistry. It has a magnetic field, thick oceans, and an atmosphere that protects and regulates. It has plate tectonics that recycle nutrients and maintain climate. It has survived long enough for complex ecosystems and intelligence to arise. Remove any of these, and the story ends. This is why the universe feels empty, even though it is full of worlds. It is not empty of matter. It is empty of places where matter can become alive and stay alive for billions of years. The stars are beautiful, but they are not homes. Earth is. From a distance, Earth looks small. It is a pale sphere suspended in darkness, but that image is deceptive. Earth is not small in meaning. It is vast in everything that makes life possible. Every breath you have ever taken, every thought you have ever had, every story ever told has unfolded on that single world. All of human history is a thin layer on its surface. When people talk about leaving Earth, they usually mean escaping it. They imagine a future where humanity spreads out and becomes safe by not being in one place. But the physics of the universe points in the opposite direction. Earth is not a fragile egg in a hostile cosmos. It is a rare fortress in a violent sea. Everything we have learned about space tells us that Earth is not easily replaced. The atmosphere that holds oxygen is not common. The magnetic field that deflects radiation is not guaranteed. The stable climate that allows liquid water for billions of years is not typical. These things exist here because of a unique chain of accidents that happened at the beginning of the solar system. If Earth were slightly smaller, it would have lost its atmosphere. If it were slightly larger, its surface gravity would be crushing. If the moon were absent, the planet tilt would swing wildly, causing extreme climate changes. If Jupiter were not present, it would not deflect many incoming asteroids. If the sun were more active or more massive, Earth would be sterilized. There is no reason to think another planet has this same combination. When people imagine colonizing Mars or building habitats in space, they are imagining engineering solutions to planetary scale problems. But engineering does not scale that way. You cannot build an atmosphere around a planet. You cannot easily generate a global magnetic field. You cannot create a stable climate. These are the results of planetary physics, not human design. A dome on Mars is not a world. It is a life support system that must never fail. A station in orbit is not a habitat. It is a bubble surrounded by vacuum and radiation. Every second it exists only because machines are working. Earth exists because nature built it that way. We have spent centuries trying to leave this planet. In that time, we have learned something unexpected. The more we explore, the more unique Earth appears. Earth is not simply a place where life happens to exist. It is a system that has been slowly tuned by physics and chemistry over billions of years to support complexity. Every breath you take is part of a planetary machine that has been operating since long before humans appeared. The air in your lungs was once dissolved in ancient oceans. The oxygen was released by microscopic organisms that lived hundreds of millions of years before the first animals ever walked on land. The nitrogen was trapped by bacteria that turned an otherwise poisonous atmosphere into something breathable. The carbon that makes up your body passed through stars, rocks, plants, and countless other organisms before becoming part of you. This is what people forget when they talk about leaving Earth. They imagine Earth as a rock with air on it. In reality, it is a living chemical engine that constantly repairs itself. It regulates its temperature. It balances its gases. It recycles its nutrients. It absorbs impacts. It heals from disasters. A planet is not a place. It is a process. When a volcano erupts on Earth, it releases carbon dioxide. That warms the climate. The warming increases rainfall. The rainfall accelerates weathering of rocks. That weathering pulls carbon dioxide out of the air and locks it into minerals. Over time, the climate cools again. This feedback loop has kept Earth from turning into a runaway greenhouse like Venus or a frozen wasteland like Mars. No human designed this. It emerged from the interaction of geology, chemistry, and biology over billions of years. When the sun brightens, as all stars do with age, Earth slowly adapts. Plants draw down more carbon. The climate shifts. Life migrates. Oceans absorb more heat. The planet responds. A space habitat cannot do this. A sealed dome does not evolve. A machine does not self-correct unless it was programmed to. And no one can program a system to anticipate every possible failure over centuries or millennia. Every artificial environment humans have ever built has depended on constant intervention. Even the most advanced greenhouses require maintenance. Even the most automated factories break down. Even the most sophisticated life support systems fail if neglected long enough. A planetary biosphere does not require a control room. It does not require technicians. It simply works. This is why Earth has remained habitable for billions of years, while every known artificial system fails in decades at best. When people imagine space colonies, they imagine technology replacing nature. But technology is not more reliable than nature. It is far less so. A machine can be precise, but it is not resilient. A planet is imprecise, but it is incredibly robust. If one forest burns, another grows. If one species dies, another fills its niche. If one region freezes, another remains warm. The biosphere adapts because it is not centralized. A space colony is the opposite. It is centralized. All the oxygen is in one place. All the food is in one place. All the people are in one place. All the power systems are in one place. This creates a single point of failure for everything. On Earth, there is no single point of failure. Even a global catastrophe like an asteroid impact does not destroy the entire biosphere. Life retreats. It changes. It survives. In a space habitat, a single cracked wall, a single failed pump, a single contaminated water tank can kill everyone. This is not a question of how advanced the technology is. It is a question of scale. Earth is large enough that local failures do not become global ones. A colony is not. The same is true for gravity. Human bodies are shaped by gravity. Our bones form in response to it. Our muscles grow because of it. Our circulatory system depends on it. Even our inner ears and sense of balance are built around it. Remove gravity and the body begins to fall apart. Astronauts lose bone density. Their muscles waste away. Their hearts weaken. Their vision changes. Their immune systems falter. Artificial gravity can be created by rotation, but to be healthy, it must be smooth and constant. That requires structures kilometers wide. Anything smaller creates motion sickness and uneven forces. Such structures would have to be built in space and kept intact for centuries. Every meter of them adds mass. Every kilogram of mass adds energy cost. The physics never changes. Earth gives us gravity for free. It gives it to every organism everywhere all the time without any machinery. Radiation is another planetary gift. Earth's magnetic field deflects charged particles. Its atmosphere absorbs high-energy photons. Together they create a radiation, environment low enough for complex life to persist. Outside that shield, radiation damages DNA and electronics alike. Shielding can reduce exposure but never eliminate it. And shielding adds mass. Earth shields us with tens of kilometers of air and thousands of kilometers of magnetic field. No spacecraft can replicate that. Then there is water. On Earth, water is abundant. It covers most of the surface. It evaporates and rains. It flows through rivers and aquifers. It is constantly purified by the hydrological cycle. In a space habitat, every drop must be recycled. Every contaminant must be removed. Every leak is a crisis. Water becomes a fragile resource instead of a planetary system. Air is the same. On Earth, the atmosphere is vast. It dilutes pollutants. It buffers changes. In a habitat, a small change in composition can become deadly. Oxygen too high becomes flammable. Too low becomes suffocating. Carbon dioxide too high becomes toxic. On Earth, these gases are regulated by forests, oceans, and geology. In a habitat, they must be regulated by pumps and sensors. Earth is forgiving. Artificial worlds are not. This is why the fantasy of abandoning Earth misunderstands what Earth is. It is not just a location, it is a miracle of planetary engineering that no civilization could recreate. We did not build this world, we inherited it. And physics is telling us very clearly that we will never build another. The idea that humanity can simply leave Earth and thrive elsewhere is rooted in a deep misunderstanding of how rare our situation truly is. When people imagine Mars or distant exoplanets as potential new homes, they picture landscapes, red deserts, blue oceans, alien skies. But habitability is not about scenery. It is about systems. And Earth is a system that is extraordinarily difficult to replicate. Consider something as simple as breathing. On Earth, the atmosphere is constantly being renewed. Oxygen is produced by plants and algae. Carbon dioxide is absorbed by oceans and rocks. Nitrogen cycles through soil and air. The balance of gases is kept within a narrow range that allows both fire and life. This balance has existed for hundreds of millions of years. It has survived ice ages, mass extinctions, and the slow brightening of the sun. In a space habitat, this balance would have to be maintained by machines. Sensors would measure gas levels. Computers would decide what to adjust. Valves and pumps would respond. But every sensor drifts. Every computer can glitch. Every valve wears out. Over time, small errors accumulate. The system moves away from its ideal state. If no one notices in time, people die. On Earth, there is no central controller for the atmosphere. It is controlled by millions of independent processes that constantly counterbalance each other. This is why it is stable. Decentralization creates resilience. Artificial systems are centralized. That makes them brittle. The same is true for food. Earth produces food through countless ecosystems. If one crop fails, another thrives. If one region suffers drought, another receives rain. The global biosphere distributes risk. A space colony concentrates it. If its hydroponic system fails, there is no backup forest. If a fungus infects its crops, there is no wild ecosystem to compensate. Starvation becomes a real possibility within weeks. Waste recycling on Earth is handled by soil microbes, oceans, and weather. In a habitat, it must be done by a few tanks of bacteria and chemical processes. A single contamination could poison the entire system. The more you study these systems, the more it becomes clear that Earth is not just convenient. It is necessary. Then there is time. Earth has been stable long enough for complex life to evolve. That stability is not guaranteed. Many planets do not get that chance. They lose their atmospheres. Their oceans freeze or boil. Their stars flare violently. They are struck by large impacts. Earth survived all of this. It had a large moon that stabilized its tilt. It had Jupiter acting as a partial shield. It had the right distance from a calm star. Even Mars once had rivers and lakes. It lost them when its magnetic field died. The solar wind stripped away its atmosphere. The water either escaped to space or froze underground. Today, Mars is a cold desert, not because it was unlucky, but because it lacked the long-term planetary systems Earth has. Terraforming Mars would mean recreating those systems. It would mean rebuilding an atmosphere thick enough to breathe. It would mean generating a magnetic field strong enough to protect it. It would mean warming the planet without triggering runaway greenhouse effects. It would mean restoring water to the surface. Each of these tasks alone is beyond any technology humans have. Together, they require control over planetary scale physics. Even if such changes were possible, they would take thousands or millions of years. Human civilizations rise and fall in centuries. We cannot manage projects on those timescales. Earth built itself over billions of years. We do not have that luxury, so when people say humanity must become multiplanetary to survive, they are projecting a fantasy onto a universe that does not support it. There are no easy second homes. There are only harder versions of the one we already have. Every probe we send and every telescope we build confirms this. The more worlds we find, the more hostile they appear. Earth does not look typical. It looks exceptional, and that has a sobering implication. It means that if we damage this planet, there is no backup. There is no escape hatch waiting in the stars. The universe is not offering us another cradle. It gave us one, and that one is all we have. When people talk about the future of humanity, they often imagine it spreading outward like a wave, filling the galaxy with cities and civilizations. This image is powerful because it mirrors our history on Earth. We spread across continents, we crossed oceans, we built nations on distant shores. It feels natural to assume that space is simply the next ocean, but the physics of space is not the physics of Earth. On Earth, the distance between two places is measured in days or weeks of travel. In space, the distance between stars is measured in years, even at the fastest possible speed. That difference is not just quantitative, it is qualitative. It changes what it means to be connected. A human civilization is not just a group of people. It is a network of communication, trade, culture, and shared knowledge. It depends on feedback. Ideas spread, technologies improve, resources flow. When something goes wrong, help can arrive. That is what makes civilization possible. The speed of light breaks that network between the stars. If two worlds are separated by 10 light years, then a message takes 10 years to travel one way. A conversation takes 20 years. By the time a reply arrives, the situation has completely changed. Political decisions become impossible. Scientific collaboration collapses. Emergency response is meaningless. This means interstellar societies cannot be unified. They cannot coordinate. They cannot share resources in any practical way. Each world becomes its own isolated bubble, drifting through time. A colony around another star would not be an extension of Earth. It would be a different civilization entirely. Over centuries, its language would change. Its culture would change. Its biology might change. Earth would become a myth, not a home. This isolation makes interstellar colonization far more fragile than it appears. If a distant colony experiences a disaster, there is no help. If it develops a dangerous technology, there is no way to regulate it. If it collapses, there is no rescue. On Earth, even remote regions are part of a global system. Food, medicine, and information move across the planet in days. That is why disasters can be survived. That is why knowledge accumulates. That is why progress happens. In space, there is no global system. There are only islands. This also means that even if a few star colonies existed, they would not preserve humanity. They would fragment it. Each world would drift into its own evolutionary and cultural path. Over time, they would no longer recognize each other as the same species. The dream of becoming a galactic civilization assumes that physics allows a galaxy to function like a large country. It does not. The speed of light makes that impossible. So what we are left with is a universe that allows observation, but not connection. We can see distant galaxies. We can detect planets around other stars. We can listen to the echoes of the Big Bang, but we cannot go there in any meaningful way. We are confined to our small island of space-time. Earth is not just where we started, it is where we are. And the deeper we look into the universe, the clearer that becomes. There is a quiet assumption behind many visions of the future. It is the belief that technology always improves, that whatever barriers exist today will eventually fall, that what seems impossible now will become routine later. This assumption has worked well on Earth. We went from sailing ships to airplanes, from telegraphs to the internet, from hand tools to supercomputers. It feels natural to project that trend into space, but technology does not exist in a vacuum. It exists inside physics. Every technological breakthrough we have ever achieved has operated within the same fundamental laws. We learned how to use electricity. We learned how to manipulate chemistry. We learned how to harness nuclear reactions. But we did not change the laws of thermodynamics. We did not alter gravity. We did not bend the speed of light. Those rules are as absolute today as they were at the beginning of the universe. Space travel is constrained by those rules. No amount of ingenuity can make mass move without energy. No amount of engineering can make information travel faster than light. No amount of shielding can eliminate cosmic radiation. No material can survive infinite time without degradation. This is what sets space apart from every frontier humanity has ever faced. On Earth, when we encountered an obstacle, we could often go around it. A mountain could be crossed. A sea could be sailed. A desert could be traversed. Space is not an obstacle in that sense. It is a condition. It is the fabric of reality itself. The stars are not separated by empty space. They are separated by time energy and causality. Those cannot be engineered away. This means that no matter how advanced our technology becomes, Earth will remain central. It will always be the only place where humans can live without machines keeping them alive. It will always be the only place where children can be born without radiation exposure. It will always be the only place where ecosystems can exist without human intervention. Every off-world habitat would be a dependent system. It would survive only as long as its technology does. A single failure could end it. Earth has survived supervolcanoes, asteroid impacts, and ice ages. No space colony could survive even a fraction of that stress. So the idea that humanity can abandon Earth misunderstands both technology and nature. Technology can extend us. It can allow us to visit space. It can allow us to build small outposts. But it cannot replace a planet. Earth is not a stepping stone. It is the foundation. There is a quiet truth hidden beneath every image of the stars, a truth that becomes clearer the more deeply we learn how the universe actually works. When humans first looked up at the night sky, the stars seemed close. They felt like lights on a dome, like distant fires that could someday be reached. As science advanced, that illusion slowly died. We learned that each star is a sun, that each sun is separated from every other by distances so vast they are measured in years of light. We learned that between those suns there is not a welcoming emptiness, but a hostile expanse filled with radiation, debris, and energy that slowly erodes anything that dares to pass through it. And as our instruments became more powerful and our theories more precise, a deeper realization emerged. The universe does not want to be crossed. It is built in a way that makes connection rare and isolation inevitable. Every star system is its own island. The space between them is not simply empty distance. It is time itself. Light takes years to cross even the smallest interstellar gaps. Matter takes far longer. A ship moving faster than anything humanity has ever built would still require tens of thousands of years to reach the nearest star. Even at speeds approaching the limits allowed by physics, the energy required becomes so immense that no realistic machine could supply it. This is not because engineers have not tried hard enough. It is because the laws of physics make it so. Energy rises with speed. Mass resists acceleration. Relativity increases inertia as velocity climbs. At some point, the universe simply refuses to let you go any faster. Even if a ship could somehow reach those speeds, the environment would become deadly. Tiny grains of dust would strike like high explosive weapons. Cosmic rays would tear through the hull and through human tissue. Electronics would slowly degrade. DNA would mutate. Every second of the journey would be a slow grind against entropy. Time dilation might make the trip feel shorter for the crew, but it would not protect their cells or their machines from damage. The universe would still take its toll. And if by some miracle a ship arrived, it would arrive alone. All communication with Earth would be delayed by years or centuries. No rescue would ever come. No advice would arrive in time. The travelers would not be explorers. They would be exiles, stepping into a future where everything they knew had vanished into history. This is the part of space travel that science fiction rarely confronts. It is not just about getting there. It is about what it means to be there. Human beings are not built for isolation on that scale. We are social creatures whose minds and cultures depend on constant exchange. A civilization is not just a collection of bodies. It is a network of information, trade, cooperation, and shared memory. The speed of light breaks that network between the stars. It turns every distant world into a separate timeline. Over time, those timelines would diverge until they no longer recognize each other. So even the dream of a galactic civilization collapses under physics. The universe allows observation. It does not allow unity. Against this backdrop, Earth appears in a new light. It is not just where we happen to live. It is one of the very few places where the universe has created the right conditions for complexity to endure. Earth is wrapped in a magnetic field that deflects radiation. It is covered by an atmosphere that traps heat while allowing excess energy to escape. It has oceans that regulate climate and dissolve carbon dioxide. It has plate tectonics that recycle nutrients and prevent runaway greenhouse effects. It has a large moon that stabilizes its tilt and moderates its seasons. It orbits a stable star that does not flare violently. These features are not common. They are the result of a long chain of cosmic accidents. The more exoplanets we discover, the more this becomes clear. Most worlds are either too hot or too cold. Many have no atmospheres or ones that are poisonous. Many are blasted by radiation from active stars. Many lack the geological activity needed to regulate their climates. Earth does not just fall into the habitable zone. It occupies a narrow sweet spot of physics, chemistry, and history. When people imagine terraforming or building off-world colonies, they imagine replacing these planetary systems with technology. But technology does not have the same resilience as a planet. A life support system must work every second. A pump must not fail. A filter must not clog. A computer must not glitch. A small error can kill everyone. A planet has no single point of failure. It absorbs shocks. It adapts. It recovers. Earth has survived impacts that would obliterate any space habitat. It has survived ice ages that would freeze any artificial colony. It has survived mass extinctions that would wipe out a closed system. Life endured because the planet endured. This is why the idea of leaving Earth to survive misunderstands where our strength comes from. Our strength does not come from technology. It comes from living on a world that supports us without asking anything in return. The universe beyond Earth is not cruel in any intentional way. It is simply indifferent. It follows its laws. Those laws produce stars and galaxies and black holes. They also produce radiation and vacuum and isolation. Life appears only when those forces happen to cancel out just enough for complexity to take hold. Earth is one of those rare cancellations. We should not see that as a limitation. We should see it as a gift. The stars are beautiful. They inspire wonder. They teach us about the origin of everything. But they are not waiting for us. They are not calling us to settle them. They are distant fires in a universe that is mostly hostile to fragile things. We are fragile things. And yet here we are, alive on a world that for billions of years has protected us from the very cosmos that created us. That is not something to abandon. That is something to understand, to cherish, and to defend. Because in the end, after all the equations and all the telescopes and all the dreams of distant worlds, one truth remains. Earth is not just our home. It is the only harbor we will ever have.